Some of you have requested some extra practice problems, and so here we go. I'm going to give you some insights as you do your extra thermo problems. So as we know, the definition of temperature is the average kinetic energy of particles in a sample. Because this is an average, it is independent of the size of the sample. Thermal energy, on the other hand, is based on a total consideration of temperature and mass of the sample. And so if you have a higher temperature, you have higher thermal energy. But also if you have higher mass or more substance present, you're going to have a higher thermal energy. Now when we look at the next problem, it's important to realize what equation we have to use. So here we want to notice that we are increasing the temperature from 10 degrees Celsius to 40 degrees Celsius. This is a temperature change problem. So whenever we have that, we're going to use Q equals mc delta T, where our Q is the heat, that's what we're looking for. Mass, in this case, is 200 grams. Specific heat capacity, this indeed is water, so we're going to use our 4.18 joules per gram degrees Celsius. And our change in temperature here we can see is going to be 30 degrees because we're going from 10 degrees up to 40. So we're going to have a 30.0 degrees Celsius temperature change. When we put this in our calculator, we're going to get a Q that's pretty big, so we'll probably want to mention that in scientific notation. We're going to do a scientific notation of Q equals 2.51 times 10 to the 4th joules. So again, for our next problem, again, our biggest challenge is to decide which equation we're going to use. So for this one, we're looking at the water vaporizing. And when we vaporize, we're going to use Q equals mH where this time we're given the Q, 1.00 times 10 to the 4th joules, and that is equal to the mass that we're looking for. And the HV you can always look up on Table B in your Regents reference sheets. You'll see for HV we have 2,260 joules per gram. And so when we do that calculation, we're going to get a mass of 4.42 grams. Again, algebraically, you're going to take your 1.00 times 10 to the 4th and just divide it by 2,260 to get your answer. Okay, for this next problem, we're asked to draw a heating curve, so still very important that we can do this. Remember, a heating curve is going to basically graph our temperature versus heat added, or time you might see here sometimes. So if we have water, remember we're going to start out at negative 20 degrees Celsius. That water is going to be a solid, and we're going to have to increase its temperature, giving us the slanted line, until it hits its melting point at 0 degrees Celsius, in which case our line is going to flatten off as it melts. Then from here, after all of that water has melted, it's going to increase its temperature again till it hits the boiling point. And then it's going to boil. Now notice I'm going to make this line a lot longer than the melting line because it takes more energy. That heat of vaporization is much higher than the heat of fusion. And then I'm going to go ahead and increase my temperature of that gas up to 120 degrees Celsius because that's what they wanted me to do in the problem. Now I also have to understand what types of energies are changing. So remember, on every slant, we're going to see kinetic energy increasing. That's why it's a slant. Kinetic energy is our temperature increasing. And whenever one form of energy is increasing, that other potential energy, in this case, is remaining constant. The flats, however, is going to involve a change of potential energy. So here, we're going to have our potential energy increasing and our kinetic energy remaining constant. And up here again, while we're boiling, we have potential energy increasing while our kinetic energy is going to remain constant. Again, just another really important thing to remember, and that is that this flat, the melting flat portion, is going to be smaller than the boiling flat portion because it takes a lot more energy to boil than it does to melt. All right, here we see another mathematical problem, and this time they're asking us for information about melting. And so whenever we melt, we're going to use the Q equals mHF equation. This time they're looking for Q. They're giving us a mass of 56.6 grams. And this indeed again is water. And so we remember we can look up the HF of water, but it is 334 joules per gram. And when we multiply those two out, we're going to get a Q value of 1.89 times 10 to the fourth joules. Again, I typically like to use scientific notation for numbers that are in the 10,000s. Okay, let's have a look at problem number 6. Here again we see that there is a temperature change occurring. So we're going to use our Q because I'm C delta T equation. We're going to put in 5.02 times 10 to the third joules for our Q. Our mass is what we're solving for. This is water, so we're going to use our 4.18 joules per gram degrees Celsius for the specific heat of water. And we can see pretty clearly here to go from 10 to 30 degrees Celsius is a 20.0 degrees Celsius temperature change. When we do the algebra and we solve for m, essentially taking 5.02 times 10 to the third divided by 4.18 divided by 20.0, we're going to get a mass equal to 60.0 grams. Okay, problem number 7. Problem number 7 is asking for a final temperature, so we must have a temperature change going on here again. So we're going to use our Q equals mc delta T. We have 4,210 joules of energy equal to a mass of 50.0 grams. Again, this is water, so we're going to use our 4.18 joules per gram degrees Celsius. And this time, instead of putting in our temperature that they give us of 22.5, we're going to actually solve for the delta T first. When we do that algebraically, we take 4,210 divided by 50 divided by 4.18, we're going to get a delta T equal to 20.1 degrees Celsius. So when we notice here that we're heating our substance, if we started at 22.5 and we're increasing our temperature by 20.1, we're going to simply add those two temperatures together to get our final temperature. So our final temperature here is 42.6 degrees Celsius. For our next problem, problem number 8, they're asking us to go to table I. Table I is where we can find a lot of reactions. At the top, we find our combustion reactions. And when we look there, if we're looking for the one that's most endothermic, we're looking for a negative delta H, because that would be what is exothermic, and we want to find the biggest number we can. When we look, we'll see the biggest number in the combustion reaction section is 10,943 kilojoules. And that is for the reaction of the combustion of octane, C8H18. Remember, combustion always has oxygen, this case 25 oxygen molecules, and it always produces carbon dioxide and water. Again, I'm just copying this straight off of table I. Number 9 is another problem that requires us to look at table I, but this time we're looking at the bottom section of table I. When KNO3 dissolves, we want to look at the delta H. The delta H for that solution or dissolving of KNO3 is a positive delta H. So when I look that up, I see positive. If I forget what positive means, I can look at the bottom and see that negative means exothermic, so positive means endothermic. And whenever something is endothermic, it's taking in energy from the surroundings. In this case, water is a good portion of those surroundings. So if water is giving up some energy to get that stuff to dissolve, the temperature will decrease. Okay, for problem number 10, whenever we're asked about kilojoules and we're given a mole amount that we can tell is a reaction that's happening, we want to kind of set this up like a dimensional analysis problem. So I'm going to start with the number that they give me, 7.25 moles, and I'm going to pay attention to the NO because that's going to be important. And I'm going to come over here and I'm going to remember that I'm trying to get to kilojoules. So the next step would be to access table I for the reaction that is forming or synthesizing NO from its elements. When you go to table I, you're going to see that reaction. And in front of the NO in that reaction, you will see a coefficient of 2. That coefficient has to be what we use with our moles of NO to get those two to cancel. So again, very important that you use the coefficient from the balanced chemical equation because that's what the kilojoule amount goes with. When we look at our delta H for that reaction, we're going to see 182.6 kilojoules. So since I'm where I want to be, I'm ready to do the math. 7.25 times 182.6 divided by 2 is going to give me 661 kilojoules. So in number 11 here, we have a very similar problem to number 10. Again, we're being asked for kilojoules. And this time they're using aluminum as our start point. So I'm going to start there, 5.00 moles of aluminum. I'm going to go over here and remember that I want to get to kilojoules. And I have to look up on table I whatever reaction they're describing. So they're describing the synthesis of aluminum oxide. So I'm going to look at that synthesis reaction, and when I do that, though, I have to remember that the information I was given was about aluminum. So I find the aluminum in that reaction, and I see a 4 coefficient in front of that aluminum. And that's the coefficient that's going to go with my 3,351 kilojoules that I see on table I to go with that reaction. Simple as that. I'm ready to do the math. 5 times 3,351 divided by 4. I'm going to get 4,190 kilojoules. Okay, for question number 12, we are being asked about a potential energy diagram. So we have to know these potential energy diagrams inside and out. So if we look over here, we can see that our potential energy diagram has some reactants down here and some products that are ending up higher in energy. Whenever we see this relationship where the products are higher than the reactants, we have to remember that it is an endothermic reaction. In other words, those reactants are taking energy in and they're bumping up to a higher level when they become products. So let's make sure that we can do every numbered interval in this potential energy diagram. So when I look at number 1 here, starting at the axis and going up to that reactant line, I'm going to know that this is really standing for simply the potential energy of those reactants. When I look at quantity number 2, from that starting reactant point up to the top of the hill, that is going to stand for my activation energy, that energy that's required to get this reaction to go. And because it's starting at the reactants, it is going to be for the forward reaction that activation energy is standing for. When I look at quantity 3, from the axis all the way to the top of the hill, remember who lives at the top of this hill? I'm going to call that my potential energy of the activated complex, that very unstable substance that's between reactants and products. When I look at quantity number 4, which is right here, I'm actually looking at the position from my products to the top of the hill. This is an odd one, and it's only appropriate for reversible reactions. We'll talk more about this in our kinetics and equilibrium chapter. But here we can kind of preview that is also going to be an activation energy. But because it's an activation energy that's starting from the products to the top of the hill, this is actually the activation energy for the reverse reaction. And those times when we go from products back into reactants in a reversible reaction. More common for us in this chapter would be to look at this quantity number 5. Notice quantity 5 is the difference between the reactants and the products lines. Whenever we look at that difference, we're going to see that this is the heat of reaction. And formally, that heat of reaction is always equal to the potential energy of the products minus the potential energy of the reactants. And so it also kind of explains here why our delta H, our heat of reaction, is positive. Because if I take a bigger number for my products and I subtract it from the smaller number of my reactants, I am going to get a positive result in this case. And finally, number 6. Going from the axis up to that product line is simply my potential energy of those products. Okay, here I've cleaned things up for us a bit so that we can actually see what's going to happen when we add a catalyst to this reaction. Remember what happens when we add a catalyst? We are going to lower the activation energy. And we do that by providing an alternate pathway. So if you can kind of see my dotted line here, I am actually looking at a lower hill without changing the position of the reactants and the products. I'm simply lowering that activation energy by providing a smaller hill for that reaction to get over. Okay, when we come back here and we look at how a catalyst actually works and what it does, we remember that it's lowering that activation energy by providing an alternate pathway for the reaction to occur. Important thing to remember, it does not change the heat of reaction. An endothermic reaction will still be an endothermic reaction even after a catalyst is added. For this next question, just making sure that you understand some of those forms of energy and what they might be called in chemistry. So for heat, we typically call that thermal energy. Electron movement would be electrical energy. Any different types of lights, even the types that we can't see like UV and X-rays, those are electromagnetic energies. Changes in the nucleus of the atom would be considered nuclear energy. Anything dealing with bonds and reactions, typically we're going to call chemical energy. And things that deal with the movement or positions of matter, we call mechanical energy. All right, here we are asked to evaluate H plus H, making H2, as to whether it's endothermic or exothermic. Here you have to realize that this is really describing the opposite of breaking bonds. It's actually making a bond. It's taking two hydrogen atoms and putting them together. Whenever we make bonds, we're going to have an exothermic process. Essentially the opposite of when we were breaking the bonds in class. I'm sure you all remember that. When we have something that is exothermic, like the making bonds situation that we have here, heat is going to be produced, and therefore we put it on the product side. All right, and once more, kind of looking at that heat of reaction component. That, by definition, truly is the potential energy of our products where we ended up minus the potential energy of the reactants where we started out. Okay, and for this next one, again, we have to look at table I. They're asking about the decomposition of ammonia. We don't have decomposition reactions on table I, but we do have the opposite, synthesis reactions. When we look at synthesis of ammonia, we see that it has a negative delta H, indicating that it's exothermic. So the opposite process, decomposition, is going to have the opposite sign for its delta H, a positive delta H. And this shows that the reaction would actually be endothermic. Okay, for this next problem, you're going to have to excuse my handwriting. It's going to get ugly probably. But we're dealing with a calorimeter problem. And whenever we do that, the big idea here is that the Q of the water in the calorimeter is going to be equal to the Q of whatever other substance, in this case a metal, that we're looking at. And so we just set up the two sides of the equation for our MC delta T's, and we do the math. So the mass of the water here is going to be 50 grams, and the specific heat capacity of water, 4.18 joules per gram degrees Celsius. My delta T for the water, I have to calculate, is going to be 28.1 degrees Celsius minus where it started at 25.0 degrees Celsius. And all that's going to be equal to the mass of the unknown metal, which is 12.48 grams. The specific heat capacity of the metal, which is what we're looking for, and the delta T. I think I'll write it up and down here so that we have space. Essentially taking 99 degrees Celsius minus where it ended up, the 28.1 degrees Celsius. Okay. Now from here you can do as many steps in algebra as you want. If you want to do some multiplication first or some subtraction first and do it out that way, I simply put this all in my calculator. I would take 50 times 4.18 times parentheses 28.1 minus 25 end parentheses divided by 12.48 divided by parentheses 99.0 minus 28.1 end parentheses. And when I do all of that, and hopefully you do too, you'll be able to get the specific heat capacity of the metal at 0.732 joules per gram degrees Celsius. And I always stop and ask myself, does this make sense? And remember, metals are going to have relatively small specific heat capacities, oftentimes less than 1. And so this makes sense to me, and I'm going to call that problem good. Okay, remember that thermal energy is directly related to both temperature and mass when answering this question. So when we look at our sample that has more mass and also a higher temperature, the 50 gram sample at 100 degrees Celsius, that will definitely have more thermal energy than the other sample. And for number 19, when they're asking about the highest average kinetic energy, this is definitely just going to look at your temperatures, regardless of the size. Even if I had 1,000 grams at 75 degrees Celsius, the sample at 100 degrees Celsius will have the higher average kinetic energy. The why is simply because highest average kinetic energy is the temperature of the sample. Okay, when we look at a reaction such as we have here and we see energy written on that reactant side, we got to know that whenever energy is a reactant, it's required for the reaction to occur. It is an endothermic process. When you first look at this reaction, you might think that energy is not conserved because you only see the word energy on the reactant side. But remember, conservation of energy means that the total energy is equal on both sides. No energy is gained or lost, simply transferred to different forms of energy. So while on our reactant side, we have to remember that some of the energy is there in maybe the form of thermal energy or chemical energy. We also have the potential energy of A to add into that equation. And then those two are going to go together and they're going to equal the total potential energy of that product B. So ultimately, total energy of the reactant side is equal to the total energy of the product side. Okay, so when we're drawing a potential energy diagram for something like this, we have to remember we're always graphing potential energy, and this is often either time or reaction progress. And for an endothermic reaction, we're going to start with reactants lower than where they end up as products. That's because we put energy in to make that reaction occur. Always have a hill showing that activation energy that's required. And then finally, quite clearly, we can see from our potential energy diagram that B has the higher potential energy than A. Again, because we put energy into that endothermic reaction to make it occur. So I hope that this is helpful to some of you that needed an extra little bit of guidance, and I look forward to you doing very well on your thermochemistry test. Good luck.